Welcome all to my channel. In this video I am going to present one of my favorite topic, tensor. Since scalars can be represented by magnitude only, single numbers, and vectors by magnitude and direction, three numbers in three-dimensional space. You might suspect that there are other entities involving magnitude and directions that are more complex than vectors. That is, requiring more numbers than the number of spatial dimensions. Indeed, there are, and such entities are called tensors. Basically, tensor is the father of vector quantities, and eventually, you also agree with my opinion. Now, definition of tensor. A tensor is the mathematical representation of a physical entity that may be characterized by magnitude and multiple directions. Some favorite examples are inertia tensor and stress tensor. Unless you know the basic features of tensor, then this definition will not work. I mean to say that to understand the definition of tensor, you need to first follow some steps that I'm going to disclose in this video. So watch the video to the end, and if you like my video, then please subscribe my channel so that any video that I post will notify you and will not miss my any video. Now, without wasting much time, turn our attention to the main topic. If you look into the inertia tensor, the mathematical expression is I is equal to L by omega. Then you can see that this quantity is made up by two vector quantities. One is angular momentum L and other is angular velocity omega. Both are the vector quantities and therefore has a definite direction, both of them. Now it is possible that the direction of angular velocity and angular momentum may not be same. Consider a ball attached to a massless rod rotating as shown in the diagram. You can see that the angular momentum L is equal to R cross product of P, where P is the force, is not in the direction of omega. Now look into the stress tensor, and it is expressed by sigma is equal to F by A. It is made by two vector quantities just like inertia tensor. One is the force and another is the area. You know that force is a vector quantity, and now let me allow to show that area is also a vector quantity. In this figure, three axes are chosen: axis 1, axis 2 and axis 3. Now, the orientation of any arbitrary area may be perpendicular to axis 1 or axis 2 or axis 3. So, the orientation of area is not arbitrary and therefore a vector quantity. Another very important term while dealing with tensor is the rank of a tensor. Basically, all quantities are tensor quantity depending upon its rank. For scalar quantities, they are denoted as tensors rank of 0. For vector quantities, tensor's rank of 1, and for tensor quantities, its rank can be denoted as R, depending upon how many vector quantities are present in that tensor quantity. For example, the rank of the above mentioned two tensor quantities is 2, because two vector quantities are present in both the tensors. Now, once we fix the rank of a tensor, then we can easily say how many components are present in that tensor quantity of rank R. Let's find out. You know that for a scalar quantity, only a magnitude is required to present that scalar quantity in n-dimensional system. More precisely, only one number is required. For a vector quantity, you require n numbers to present that vector quantity in n-dimensional system, and also these n numbers are the components of that vector quantity in n-dimensional system. For example, velocity is a vector quantity and it has three components, Vx, Vy and Vz. Suppose in three-dimensional system such as x, y and z. Now, to present tensor quantities, n to the power r numbers are required, where n is the dimensions and r is the rank of a tensor. So, 3 to the power 2, that is equal to 9 numbers are required to present a tensor of rank 2 in three-dimensional system. So, in three-dimensional space, they look like this. Now, from the above expressions, you can see that in a three-dimensional space, a vector quantity has only 3 components, but a second-order tensor has 9 components. So you decide what you call tensor quantity, father or grandfather of vector quantities. Now, from above discussions, we can conclude that number 1, tensor quantities has different magnitudes in different directions. Number 2, in tensor quantities, more than one vector quantity present. Number 3, the rank of a tensor depends on the number of vector quantities that present in that tensor quantity. Number 4, once the rank is fixed, then for n-dimensional system, the components of that tensor quantity can be found out. Now viewers, in my next video, I try to cover about some important topics such as index notation, summation convention, Knocker delta, E-permutation symbol, etc. Thank you for watching my video.